Welcome back, math nerds. It's lesson 68 time. It's mutually exclusive and inclusive events. This is a little bit of probability and statistics that we're doing today. Invented by Leonard Euler and René Descartes. I think those are the two guys. No, Pascal and Descartes. There we go. Little history for you. You're going to need your favorite pencil today. I prefer the black Ticonderogas. Excellent. Good erasers. You're going to need homework paper. You're going to want your notebook where you're going to write down notes that you can use on the test. I also have here a couple of gyroscopes. Dice actually may come in handy today just for trying things out, though you don't need them. And I got a book here today that you might want to read. Has to do with what we're talking about today. Euler, master of us all. Good read. A little thick, but it's good. Okay, let's get started. I got two pictures up here for you that are gonna basically this is all you need more or less. The rest is just details. Over here we have what's called a Venn diagram. Venn named after a mathematician, but actually Venn did not invent Venn diagrams. Should be named after him, but what else is named after the guy, so you got to give him something, right? Okay, so the actual first guy to use diagrams like this to explain things, probability and sets, is Leonard Euler. Okay, 1700 Swiss mathematician. He is so famous, he's on Swiss money. That's how important that guy is. And he's one of my heroes. This Venn diagram describes two events which are called mutually exclusive. You see that those two things don't overlap. There's no crisscross between the two of them. The book would have something like taking one die and rolling odds or rolling evens. Okay, so you only got a certain number of possibilities for that. You could say A is the event of getting an odd number when you roll the dice, and the only possibilities for that are 1, 3, and 5. And this one might be rolling an even number, and that would be 2, 4, and 6. Now, it doesn't even have to include everything that you could possibly get by rolling a die. This one could be 1 and 2, or something like less than 3 and more than 4. Okay, but those two things, they don't overlap, so they're called mutually exclusive events. We're going to go to the other camera here in a little bit to do something with rolling dice, where we have two different situations, a situation A and a situation B, and that's to kind of list all the possibilities and then figure out what's the probability of those, either one or the other event occurring when there's no overlap. Formula for that is actually pretty straightforward, and it makes sense. If there's no overlap, then the probability of events like this, what's called mutually exclusive events, would be written like this. The probability of A and B occurring, and or B occurring equals the probability that A happens plus the probability that B happens. That's the rule. Probability of mutually exclusive events. So in this case, the odds are here, we have 3 out of the 6 total ways of rolling the dice, getting odds, and we'd add to that the probability of rolling evens, which was 3 out of the 6 possibilities. And of course, that equals 1. When you roll a dice, you're either going to get odd or even. So the probability of getting odds or evens is probability of getting odds plus the probability of getting evens. Okay, and again, won't always include all the possibilities, but this one does. And an example that I'll give you of that will demonstrate that. So let me move over to the other camera and do that, and we'll come back to this other picture here. Okay, you can think of it like Venn diagram. think of it like circles and what's included in each circle. I'm going to get a couple of highlighters out here to do this. And here's our two events. Let's call this one rolling a 6 as event A and rolling an 11 as event B. And I'm going to go ahead and do anything that's A. I'm going to put it in green here today. So let's start with this. We get a sum of 6, and there's just a few of them. That's 6, 2 and 4, 3 and 3, 4 and 2, 5 and 1. So we have actually 1, 2, 3, 4, 5 of our possibilities are rolling a 6. Now altogether there are 6 by 6 in this grid of all possible ways here. So probability of rolling a 6 is 5 out of 36. Okay, we're going to use yellow highlighter for rolling an 11, and that one's pretty much done. Okay, maybe this one will work better. Rolling 11. Let's see, where are those? We've got here and there. And that's it, right? You can only roll an 11 in 2 different ways. Get a sum of 11 by going a 5 and a 6 or a 6 and a 5. And so out of the total things there are 2 out of 36 ways of doing that. And there's no overlap. See, these ones are highlighted and these ones are highlighted, but neither of them are highlighted by both green and yellow. So the probability of A or B, in this case, is the probability of A plus the probability of B, and the probability of A is 5 out of 36, and the probability of B is 2 out of 36. So we just add straight across. That's 5 and 2 is 7 over 36. And if you've got your calculator, you can turn that into a percentage or into a decimal. 7 divided by 36 is, okay, so this is approximately 0.194 or 19.4% chance that you'll get either rolling a 6 or getting an 11. Come in handy with something like Monopoly when maybe you want to land on just the right thing. You got to think about what your chances are. If any of you like to play, I can't remember the name of that game, where you roll the dice in the little bucket. Whatever, I'm having a brain moment here. Okay, so let me briefly show you our second example, at least the way that it's written. And we're going to have here again, here's event A, and here's event B. Let's go back to the other camera and talk about that other bit of circles. Okay, now let's look at this set of circles here. And you notice that there's set A and there's set B, but there is some overlap between the two of them, which would be things that are both A and B types of things. So maybe when we roll the dice, we say event A is at least one of the dice is a 6. Okay, and then event B is getting a sum of 9 or more. Now there's going to be some overlap between those two events. There's some that will not be A or B. There's some that will be both A and B. Or maybe as you pull into the parking lot over by Best Buy, and Best Buy has a camera on the door, and they find out how many people come to their store. And then Petco does too, how many people come to their store. But they find out that the total number of people in that were in the parking lot was less than everybody that they came into Best Buy and everybody that came into Petco. There's some people that went to Best Buy and to Petco, and you don't want to count them twice. Okay, if you want to know the total number of people that came into the parking lot, you don't want to count them twice. So let's say you do count everybody that's in A, and then you count everybody that's in B. These guys in the middle got counted got counted twice. Okay? And so what we have to do the probabilities for this type of situation, which is called inclusive, is probability of A or B, in this case, is equal to probability of A and the probability of B, and then we take away the probability of A and B. Same thing works with like how many things. You just say the number in A and the number in B minus the number of things in the middle, and there you've got your probabilities. So this is the part where we're taking away once the thing that we have double counted. It's easier just to count everything in A and B and then take away one of our overlaps, and then we'll have all of this. In a sense, it's as if we do this. Check off the overlap so that there's only one of them there. We only want to count everything once. So let me go to the other thing, and we'll do that with the dice, just as an example of another situation where we have something where there is overlap. That's another way of saying what inclusive is. There's always going to be some overlap involved. So event A is going to be rolling at least one odd. And let's go ahead and find all those. Anything with a 1 in it. It's at least one odd. Sometimes there's two odds. Let's see, there's an odd. That's got at least one odd. So does that. Okay, ones, all the ones. 2, 3, anything with 3 in it, right? At least one of those. And we got the things with 5s. Oh, and 3s go this way as well. To me, this is easier than trying to list them all in my head. So there's 36 total things in here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. 27 is what I get there out of the 36. Okay. And then we'll go over here to a sum of 8. There aren't a whole lot of those. There's none in the first row. This is right here. There's a sum of 8. And then this one as well. And we'll go slanty-wise across the thing, and we find all of our sums of 8. So total sums of 8, 1, 2, 3, 4, 5 of those. 5 out of 36. And then we need to find the ones that are both in both categories. Okay, so A's got this big old circle of everything that's green, and B's got this circle of everything that's colored yellow, but there are some that are both yellow and green, and that would be this one and this one. So we'd say the things that are in A and B is 2 out of 36. We don't want to count that twice. We don't want to count that twice. So to find the total probability of this or that, we'll take 27/36, and we'll take our 5/36, and we'll take away our overcounting 2 out of 36. So 27 plus 5, okay, 32 minus 2 gives us 30 out of 36, or 5/6, which if you want that as a decimal, 0.83. Okay, that's basically the only types you're going to have. You need to look at them and decide whether or not there's going to be any overlap. If there's going to be any overlap, you're going to take away the double counting. And if there is no overlapping, then the problem is really super easy. That's all for that. If you want to leave a comment below or send me an email, you're free to do that. I am available to you.